Hello, my name is Thomas Kleintech. Thank you for your interest in my presentation on CT scanning, the inspection of industrial parts. I will start right away in my presentation with a question. Why are CT inspections relevant to evaluate the quality of industrial parts? Look at this example of an AM part. The tubes that connect the different components are hollow. If the tubes carry a medium, then of course leak tightness of the tubes will be of relevance. Leak tightness is of course also related to the wall thickness, and instead of doing a local measurement, you want to know if a certain wall thickness is present all over the surface of the tubes. Then of course blockages might be an issue for this part, as these will prevent media from flowing through the tubes. The parts are often connected to other parts and stresses might act on those connections. So here it can also be relevant to make sure that the material isn't weakened by inhomogeneities, especially close to those connections. And also the overall shape of the part can be important. For instance, if the part needs to be connected in a larger assembly and there are tight tolerances regarding the position of these connectors. For all these kinds of quality-related topics, CT can be a valuable inspection tool. CT stands for computed tomography. As CT is also commonly used in human medicine, in industry it is often referred more precisely as industrial computed tomography. Now, how does a CT inspection work? It is important to know that CT is a kind of X-ray inspection. So for CT, one uses an X-ray source that emits X-rays towards the sample that needs to be inspected. The sample then absorbs some of the X-ray radiation so that the intensity of the X-rays is reduced based on the amount of part material, so that is based on the penetrated wall thickness. If one then captures the X-rays after they passed through the sample on a screen, and the screen can be an X-ray sensitive film or a digital detector, one will see the X-ray image of the part. The contrast in this image depends on how much radiation was absorbed as the X-rays passed through the sample. This is therefore also called the absorption contrast. To minimize the amount of material that needs to be penetrated by the X-rays, one would actually typically place such a kind of sample in a more upward orientation. The X-ray image shows the full part geometry as it is projected into a 2D image. That's why this is also called an X-ray projection. So far, this is all 2D X-ray imaging. For CT, however, the part is rotated around its axis and X-ray projections are captured while the part rotates. This is what it looks like while the machine operates. The result are hundreds or even a few thousand X-ray projections that were taken at different steps during the part rotation. So this is a lot of image information that takes several gigabytes of hard disk space. The number of images and the time it takes for each individual image to be captured are important CT parameters. The number of X-ray images describes how many individual steps were taken during the 360-degree rotation. More images means a shorter step width and a better database for the following step. However, taking more images makes the scan notably slower, which results in longer machine time, larger costs and less throughput. Nobody will look at the hundreds or thousands of X-ray images to inspect a sample, and you may already wonder how the CT data that you might be familiar with is actually being generated. For this, all these image files are being fed into a computer algorithm that is called back projection, or more precisely, filtered back projection. I will not go into detail here, but the algorithm does exactly what its name suggests. Based on the X-ray projections, it concludes back on the 3D geometry of the scanned part. The result is then a reconstructed virtual volume model of the scanned sample. Here you can see the visualization of such a virtual 3D volume model. If you work with CT data, this will very likely look familiar to you. There are slice images, and one can browse through the data to look at internal features in any desired virtual plane of section. Further, it's also possible to view the CT scanned part as a 3D computer rendering. This 3D data can also be used in further processing steps, for instance in reverse engineering, that are not in the focus of this presentation. One can navigate through these images and hence evaluate and measure the internal features of the part. Since this is all done on a virtual 3D volume model of the actual part, this process is non-destructive, of course. Besides looking at the virtual slice images, the 3D volume can also be used to measure geometrical features of the part, both internally and externally. A common application for this is shown here, wall thickness analysis. The color mapping on the part represents variations of wall thickness over the 3D part geometry. So, coming back to the slide I showed at the beginning of the presentation, you can see that all these different quality-related questions can be answered either by looking at the virtual slice images or by performing analysis on the 3D volume of the CT dataset. For the second half of my presentation, I will answer some questions that are commonly asked by our customers. How good is the resolution of a CT scan and which details can you see? Does CT scanning work with any material? And of course, how expensive is a CT scan? First, I will start with the resolution of a scan. Keep in mind that the 3D volume of the sample is reconstructed based on digital X-ray images of the part while it rotates. The resolution of these X-ray images will determine the resolution of the reconstructed 3D volume. Resolution in that sense means how large an individual pixel in these images is. The smaller a pixel, the higher the resolution. This depends on the number of pixels that are available on the detector of the CT setup, that is the detector resolution. And it also depends on the dimensions of the part that is projected onto the finite number of pixels that are available on the detector. So generally, for a large part, the resolution will be rather low compared to a small part where you zoom in much and can see smaller structures. This principle is the same as in digital photography. If you take a picture of a complete ruler, each pixel on the image sensor of your camera needs to account for a larger area compared to if you only take the picture of one side of the ruler. With the CT equipment that we have available, we can scan with pixel sizes on the detector of 1 micrometer for very small samples. On the other end of the scale are large samples that we scan with approximately 160 microns in a worst case. The second question I would like to focus on is on the applicability of CT to any material. Again, keep in mind what CT is. A 3D volume is reconstructed from X-ray image data, and to produce the X-ray images, the X-ray radiation has to penetrate the material. Some of the radiation is absorbed, while the remaining radiation is captured and results in the X-ray image. If all radiation would be absorbed by the part, we would not see much in the X-ray image because then no X-rays were captured by the detector. How much a material absorbs X-rays depends on its atomic number, which can be read from the periodic table of elements. Here are some chemical elements that are found in many materials and their atomic numbers. If one looks how these chemical elements let X-rays pass through, you might already know that lead with an atomic number of 82 can be used to shield X-ray radiation. That is, this material has such a high X-ray absorption that it cannot be penetrated by X-rays anymore. Because of this, it will be impossible to CT scan a part that is made out of lead, unless it is very, very thin-walled. As a generally applicable principle, the penetration by X-rays is better for materials with low atomic numbers. Plastics are based on carbon polymers, and these can be CT scanned very well. It is very important to mention that this relationship is not linear, but that the atomic number affects the X-ray attenuation exponentially to the 4th power. That is a huge impact, and it makes a big difference for the outcome of a CT scan from which material a part is made. With our equipment, for aluminum, we can CT scan parts with wall thicknesses up to approximately 300 mm, while for steel we are limited to only about 50 mm. Now, the final question that of course will be very relevant for you if you consider to ask for a CT inspection of a sample: how expensive is it? We at Tpw, or in German Tpw, are a service provider. We do not sell machines or software, but we provide CT scans as a service to customers. For this, we calculate the costs based on time it takes in the machine to capture all the X-ray images, and then also on the time it takes for the operator or inspector to extract all the information that is relevant for a particular inspection project from the data. So there is a lot of diversity here, and a CT scan can be as cheap as less than 50 euro per part, but also as expensive as more than 1,000 euro per part. This is depending on the dimensions and geometry of the sample, the material from which the sample is made, the required analysis, and the quality level. With the latter I mean how much effort it takes to visualize the feature of interest. It is of course much easier to see a large chunk of material blocking a channel than finding a very thin crack that has a size close to the resolution limit of the scan. So for each part and inspection request, the price is individually calculated. If you have questions on this, or you are interested in a quotation for a specific project, or you would like to learn more about CT inspections, please feel free to contact me directly. My contact information can be seen here. With this, I would like to thank you for your attention and for listening.